Assalamu alaikum guys, welcome back. Okay, so now in this video we are going to start out a new chapter, period 3. Okay, period 3 is a chapter of inorganic chemistry and a very important chapter and very frequently tested chapter. So let's get started. Alright, so first of all you must know what a period is. Period means the horizontal row in the periodic table, you know that already. Period 3 means if you start out from here, this is the first, this is the second, this is the third period. The third period of the periodic table is called the period 3. Okay, this one. And now in this third period, these are the elements which are present. They start out from sodium, proton number 11, and they end up over here at proton number 18. Okay, so from sodium to argon. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Sodium, magnesium, and aluminum, these three are solids and metals basically, metal solids, and the remainder are non-metals. The silicon over here is a metalloid. It's a metalloid, okay, metalloid, written it over here, and the remainder are non-metals. And in the non-metals, the phosphorus and sulfur are solids, and chlorine and argon are gases. So you can find all three states of matter in here, except for liquids. Actually you cannot find liquids in here, but these are the gases. So only solids and gases are present in here. Now first of all, let's look at a few trends, a quick revision, because we already covered this in our beginning videos of this course, but still let's look at these trends. Atomic radius, let's look at atomic radius. Atomic radius, as we go across the period, it shrinks. Okay, the atomic radius shrinks, and the reason behind that has already been explained in the starting videos when we were doing atomic structure and ionization energy, but I'll still review this. Okay, why does the atomic radius shrinks as we go across the period? Any suggestion? I'll explain it to you. Basically, as we go across the period, the proton number, it increases, right? Sorry about that. Proton number, it rises. If the proton number rises as we go across the period, then what happens? Proton number rises, but the shielding effect, what's happening to the shielding effect? It's going to stay constant, right? Remember the shielding effect? What was the shielding effect, by the way? Shielding effect is basically the repulsion provided by the inner shell electrons, or the shielding provided by the inner shell electrons to the outer shell electrons. Okay, basically if you've got a nucleus over here and you've got an electron outside and you've got several shells inside and you've got certain electrons over here on the inside, these electrons are negatively charged and the outer shell electron is also negatively charged. What these inner shell electrons, and the nucleus is positive, so the inner shell electrons, they repel the outer shell electron and prevent the nucleus from attracting it towards itself, right? This repulsion which is provided by the inner shell electrons is called shielding effect. Okay, now as we go across the period, since the number of inner shell electrons is constant, it's you've got a total of 3 shells in every element of period 3, right? Because the number of shells present in an element is the same as the number as this period. So the shielding effect is constant. Shielding effect is constant, but the proton number is gradually increasing as we go across the period, meaning the nuclear charge, this nuclear pull or nuclear attraction or nuclear magnitude of attraction is increasing. Therefore the outer shell electrons, they are more tightly attracted to the nucleus. Therefore the radius, it shrinks as we go across the period. Clear? So how the radius changes as we go across the period? It decreases. And why does it decrease? First, because the shielding effect is constant. Second, because the nuclear charge is increasing. And third, so the electron density around the nucleus, it is pulled towards the nucleus. Okay, there's a net attraction and hence the electron density shrinks, atomic radius shrinks. Okay, so generally the atomic radius decreases except for argon. Argon is an exception, remember I told you, because argon is a noble gas and its atomic radius is not measured using the same technique as it is measured for these atomic gases. Okay, reason, because atomic radius is measured by the bond length, by the internuclear distance. Okay, this bond length that you have in between two atoms, the half of that bond length is going to be the radius. But in case of argon, you don't have diatomic molecules, right? That's the problem. You only have monoatomic gases. So monoatomic means you cannot measure the bond length. Therefore there is a separate technique, it's called a van der Waals radius, okay, VDW radius. Since the type of radius is different, therefore it's not following the trend, rather it is an exception, and this applies to all the noble gases, by the way. Okay, there will always be an exception in the noble gases. So now this was a quick recap, and this is what you've already covered in your previous classes as well of atomic radius, and it is done. Okay, Then comes ionic radii. Well, ionic radii, I'll discuss that in the next lecture, not here, okay. Then going on to charge density. Charge density, how does the charge density change, and what is the charge density, by the way? Charge density, remember I told you, we've already discussed this as well, but again a quick revision. Charge divided by volume is known as charge density. Okay, so charge density is the ratio of charge and volume. Remember in physics the definition of density was mass per unit volume. Charge density is charge per unit volume. So now if the charge keeps on increasing, then the charge density will rise because charge is in the numerator. Or if the denominator, meaning the volume, it keeps decreasing, then again the charge density will rise because the denominator is becoming smaller, therefore the overall answer is becoming larger. Now if the volume decreases and the charge increases, then the charge density has to rise, and that's exactly what's happening over here. Charge of the nucleus is rising as we go across the period, and the volume, meaning the radius, is shrinking as we go across the period. So both of them are happening. So therefore as we go across the period, charge density will rise. Atomic radius was falling, charge density will rise. And remember, what depends upon the charge density? The electronegativity. So electronegativity, which is the relative ability of an atom to attract the bonded pair of electrons towards itself. If the charge density rises, electronegativity will rise as well. And ionization energy will also rise as we go across the period, because remember, ionization energy, it depends upon the strength by which the outer shell electron is attracted to the nucleus. So as we go across the period, the compactness is increasing, the charge density is rising, the shielding effect is constant, nuclear charge is rising, therefore the outer shell electron becomes more tightly attracted to the nucleus, and so more energy will be needed to remove the outer shell electron. This energy which is needed to remove the outer shell electron is your ionization energy, and we've already done that in the ionization energy lectures. Now coming to the next part, yeah, we've done the solids. And by the way, silicon is a metalloid, okay. Metalloid means having some properties of metals and some of non-metals, or metalloid means something that can react with both metals and non-metals, but somewhere in between, okay. So this sums up a discussion of this lecture. In the next lecture, we are going to talk about ionic radii in detail, and then we are also going to talk about the different graphs that are made for these trends. Thank you.